will give us some answers.
Okay. So, as some of you might have noticed, I'm not Katrina, I'm her student, and this work was done under supervision. Well, I'm supposed to have a clicker somewhere, no? Yeah, whatever. Okay. I know. So,
There is one here.
no, it doesn't work. Okay. So, basically, this talk, in a way, goes as far as possible from the origin of privacy. In a sense, nothing that we will show here requires any knowledge about privacy. We're not treating privacy anymore as a tool which is with its own purpose, and which, by the way, also is a stability notion, but we're dealing only with the stability notion. Luckily for us, we had a few talks during this session, and especially Uri's now, that covered the background, so I'll just mention it in a few words and point out the notations that we are going to use. But generally, the form of the talk will be mentioning the problem, presenting the definition. I'll spend probably quite a lot of time about the notation because in a sense that's the most important part. And then see it has the nice properties we're used to get from stability notions and show that it implies and is necessary for generalization.
Do you want a ticket?
Ta-da! Thank you.
Do you?
What?
You have to first plug it in.
Yeah, that's basic logic.
But that is on computer. It just sends lightning signals to any nearby computer.
I don't know, maybe this guy listens to it.
It was you.
Okay, we good. Okay, so this is the setting. We have a distribution over the domain of sample sets. I'll mention in a moment why we're looking at the general case where the distribution is over the domain of sample sets. We ask queries about it. It can be, assessing the loss of some hypothesis or anything else. We have the true answer, which is the assessment of the query on the sample set we got. We have the true answer in the world, which is what we want. And we have a mechanism, which we'll soon define, that produces an answer. The answer, usually, if we didn't have any problems with adaptivity or with privacy, we would just think about providing the correct answer, but we might provide something else. This distance we call sample accuracy, which is a tool that it's something a quantity we can control. This is distribution accuracy, what we care about. This is generalization. As long as the queries are not overfitting, and we have generalization guarantee, the classical concentration bound, so we're good. We know that under adaptive composition, this might not be the case. And if we don't have generalization, the question is, what can we do? So, for instance, like one line of work uses some kind of bound on the whole class of queries, and it says that you have some kind of generalization guarantee for any hypothesis or any query, so then you're good. But if you don't have it, you're in trouble, and what you need is basically some form of stability notion. So that's why differential privacy is here, and that's why this talk is here. So it starts with Dwork et al. And the improved version, both in the factors and the proof of methods, which in a lot of ways we followed, and you'll see it along the way, is by the BNSSSU paper from 2016. And the main transfer theorem, probably all saw it, that guarantees that if you're both epsilon delta differentially private and epsilon delta sample accurate, then you're epsilon delta distribution accurate and up to a bunch of factors. Now, a natural question that arises once you look at it is, well, differential privacy is, in essence, a worst case demand with respect to a lot of things, and most notably the two neighboring sample sets. Right? We want to protect any person from any kind of sample set he might participate in. So for any two sample sets, we need to have a guarantee. Learning is a probabilistic process, so we usually need just that with probability greater than delta, something will happen. So it might be that differential privacy is a definition that can be relaxed and still provide generalization guarantees. There were a few, more than a few notions of relaxed differential privacy or relaxed generalization notions that were proposed along the years. The most notable one that we will refer to is the max information, because in some ways we resemble it. But again, there were a lot, and each one of them relaxed it to some degree. And then a natural question is, how much further can we relax? What's the most relaxed stability notion that we can propose that still guarantees generalization? Okay, so just the setting, the terminology we would use, because we saw different notations. So our domain is X, the range of responses is R. The mechanism receives what you used to think of as queries, but we call it generators because it generates the answers. But it might not be a query, and you will see, like, we're starting with an analysis that is a bit more abstract, and then later we deal specifically with queries. But for the intuitive level, you can look at it as a query. And we want to analyze it. Okay, so in order to speak about generalization and stability, we need to introduce the distributions into it. We need to introduce the probability aspect. So basically, there are two sources of randomness. One is the sampling of the mechanism and of the sample set. And as I mentioned before, we're dealing in the general case with distributions over the sample sets, not over the sample points. We will see it makes difference when we talk about adaptivity. And then you have the second distribution, which is the conditional distribution of the response given the sample set. Right? Every sample set induces a distribution over the possible responses based on, obviously, the specific generator that was given to the mechanism. Comment about notations. We try to put as much of the players that affect the distributions into the notation, but there's a limit to what we can put in one slide and in one paper. So, for instance, the mechanism is usually dropped because we don't deal with more than one mechanism at a time, or if we do, it's very clear. But basically, this one should also depend on the mechanism. Okay, so we have the underlying distribution over the sample sets. See?
Can the mechanism here be stateful, or is it?
We will deal with it. Right now, there's no adaptivity, but yes, the mechanisms will be able to be stateful. And it's a very delicate issue. We will touch on it later. Okay, so once we have the underlying distribution over S and the conditional distribution of R given S, well, then we can define the set of resulting distributions. So first of all, we have the joint distribution, which is the probability to get a sample set and a response as the output of that sample set. We have the what we call unconditional or marginal distribution of R, which is just, right, if we have a distribution over the sample sets and we have a mechanism that is probabilistic by itself, so it induces a marginal distribution over the responses. You have the disjoint distribution or the independent distribution, which is just, again, for a tuple sample set and a response, but the probability to get them independent of each other. And the same way we can define the conditional distribution the other way around, the sample set given in R. This is, you can look at it as a formal definition using Bayes' law, and you can look at it as, it has a meaning of, let's say, I don't know anything about the sample sets, but I got a response from the mechanism. What does it tell me about the sample set that induced this response? In a way, what's the posterior? And we will use this terminology of prior and posterior quite a lot. So I mentioned before, one relaxed, in a way, stability notion that was proposed also by Dvorak et al. Was max information. And intuitively, max information looks at these two quantities, the two distributions over the domain of sample sets and the responses, the joint and the disjoint, and it looks at the distance between them. They use the epsilon delta indistinguishability distance, and they say, well, if they're close enough, then we must generalize. There is an issue with looking at these distributions over the sample sets and the responses. It relatively naturally implies generalization, but it's not very clear if this can be also necessary, not just sufficient. Why? Because we're dealing usually with queries that are not just arbitrary queries over sample sets. The queries need to be, anyway, for guarantees, for generalization guarantees, we need the queries to be either linear queries or low sensitivity queries or some kind of query that's not very sensitive to a small change in the sample set. So maybe we have some very weird behavior happening over the sample sets, but if I can construct from it a query that assigns a specific value for a specific point, so I might still be able to generalize even if the distributions are relatively far from each other. So a more natural thing to do, and this is what we aim to do, is to move from distributions over the sample sets to distribution over the sample points. Formally, the way we define it is just by thinking of a sampling mechanism. A mechanism just as we defined all of these before, but in this case it has only one generator, which is just please give me randomly uniformly one of your sample points, and it outputs one of the sample points. It's basically the marginal distribution over sample points induced by the distribution over sample sets. There's no magic happening here. But once we have this, we can repeat just the last 5 slides, but this time with distributions over the domain of sample points and responses. Okay, so we'll just go over it formally. So what is the joint distribution over x and r? Now not x to the n and r. So it's basically running over all sample sets, the probability to get this x and this r from this sample set. Same way we can get the disjoint, it's independent, conditioning x given r, and r given x and x given r. And what's important is, even though it might not be clear from the way these are defined, they behave nicely. They have the base law. So the probability of x given r is the probability of r given x times the probability of x over probability of r. It's a lemma. It's not absolutely obvious, but it's correct. Okay, so far, no special magic done here. We just carefully defined, using a mechanism and a generator, distributions over the domain and over the range of responses and any combination of them. Okay. So when we look at it again, we can realize that basically we have now 2 distributions over x. One is d of x. It's the prior distribution. Let's say I would ask someone before the first iteration started, some all-knowing entity, some adversary, right? We're going to deal with adversary that's trying to do the worst. So let's say he knows whatever he can. And you would ask him, let's say I sampled one of the points from this sample set that you didn't see. What would it be? So he would tell me the prior. That's all you have to say. Once he saw a response, then he has a posterior. In a sense, the distance between these 2 distributions might be what will guarantee stability, right? Because in a sense, and again, Uri's talk also touched a lot about this subject. What's special about stability, more than just generalization, is the fact that not only it produces answers that are close to the correct answers, it produces answers that the probability to see them with and without a sample point, are very close to each other, right? Because if I give you if I encode all of the information in the lower order bits, so I can give you a answer that is quite accurate but still reveals too much, and any post-processing will reveal it. If I give you an answer that the probability to get it without my sample point was still very similar, it seems like nothing you can do will ever allow you to extract the information. So we say, okay, so the distance between these 2 distributions might be the key to all of it. But the question is now, which distance measure is the best way to estimate how much information was leaked? And I'm using the word information, not in the formal definition. Okay, so first formal definition we provide is the stability loss of a response. The stability loss of a response is just the statistical distance, or also known as the total variation distance, between the probability to get, it's supposed to be x, not b of x. Yeah, I just changed the notation. It's the probability to have a point in summing over all the x's in the domain, the probability the difference in the probability in absolute value, or just summing over the ones with the higher posterior than prior. In the same way, we can define a stability loss of a set, and it's just sort of averaging on the loss of the responses. I will write it down because we'll use it many times the further. So the loss defined by the underlying distribution and the generator of the R is summing over x in d plus x of R. Right? Yeah. And here's d R g x d prior minus posterior. And when it's a set.
Conditioning set, x given.
All right. And loss of a set, say b of R. We have a ton of sets, so we always use a subscript notation to say from where the set was taken. So I'm summing, okay, I'm going to be, no, yeah, it's important. Summing over the R and the b of R. D of R times L R G and G over, this is just the total probability of this questions so far?
Good. Actually, I'm lost. What's the type of...
The typo here is it's supposed to be x's, not b of x.
Oh.
Summing over the x's and the b. Not, what's b? Plus, that's... Yeah. It's all there are like a few ways to write total variation distance. One is summing over all x's, the absolute value of this distance, and then dividing by 2. Another one, it's enjoying it's always better. It's
Statistical distance.
statistical distance, yeah. And statistical distance plus typo. That's basically what's going on. You ever wondered how does their child look? Okay, and now what's local statistical stability? So a mechanism will be called local statistically stable epsilon.
So for losses, this is basically the average statistical distance over those responses, right?
If
The stability.
yeah, averaging, but averaging with the weighted average by their probability. Yeah.
Whatever, the mean.
Yeah. So this is the definition. First, two things I want to say. First of all, we know what is this set that maximizes this quantity. It's the set of all responses that are greater than epsilon, right? If you have a response with a loss that's less than epsilon, so you plug it in here, you just reduce the size. So obviously, you want to add only responses with a probability greater than epsilon. And intuitively, you can think of it as something like, let's put it here, is d rg of L epsilon r less than delta. It's not true. It's just with a factor of 2 in the epsilon, a factor of epsilon in the delta, or something like that. It's not exactly, but up to some factors, this is what it says. It says the probability to get a response for which we have a loss that is greater than epsilon is sort of less than delta. And maybe a drawing will make it seem a bit more reasonable. So let's say these are the x's and these are the r's. Right? We have responses and we have domains. So given a specific r, I'm looking at a specific r, and I'm looking at two distributions over this, product space. One is the joint distribution of x and r, and one is the disjoint, the dependent distribution of x and r. So if I'm looking at a given r, so I have two distributions. Now this is x. One is this, and another one is a bit different. And it has a statistical, some kind of statistical distance between them. The statistical distance might be small, might be big. If it's less than less than epsilon, I don't care. If it's bigger than epsilon, it's a problematic one. So if the set of responses which have a statistical distance over the two distributions that is induced by them, which is greater than epsilon, we'll call them epsilon unstable responses. If their probability is too big, then we have a problem. A few words of intuition about like what's going on here. So if these two distributions are relatively far from each other, but it's spread along all the responses, that might not be interesting. Imagine a case where for every response you have a loss, you have a difference, but the difference is like an order of magnitude of 2 delta. So overall it's more than delta when you sum, but what happens is that no matter what response you'll get, you'll have a slight degradation in the stability. That's not a problem. On the other hand, if you had a ton of degradation, but it was all concentrated in a very small set of R's, I mean negligible probability, it's also not an issue. If you have a set of R's for which the probability to get them is not negligible and the loss is also big enough, then we have a problem. That's basically the intuition behind the definition.
And here, the x, what you're plotting on the x there is a random point from the data set.
Right, right. It's the distributions we defined before all that. Okay, so we have a definition. Now, if this definition doesn't have the nice properties of most stability notions, then it's not worth anything. Post-processing, I'm just going to write it. There's nothing interesting about the proof. You can imagine if it's a stability notion over the distributions, almost all of the proofs look very similar. And it's basically, it says that any post-processing will not get these distributions further away from each other. Composition is more interesting, and we start by defining a bit more carefully what is adaptive composition. So first we need to define what is an adversary. We use A. A can be an analyst or an adversary, but we're dealing with the worst case scenario over that. Okay, so first of all, it's worth noting, I said before that differential privacy is worst case, and we don't necessarily want worst case. We don't necessarily want worst case over the sample sets because the sample sets come from a distribution. Over an analyst, we don't know what analyst we got. We might be dealing with the worst case analyst, either because he's really malicious or because some kinds of processes get the analyst to know so much that he becomes dangerous, and that's one of the open questions we'll leave to the end. It relates also to what Adam asked, like, what can we have better guarantees for analysts that are not that dangerous? Anyway, we're dealing with an adversary, so he knows everything maybe. So an adversary is a generator by itself, but this generator was an abstract concept. Now this is the first generator which actually we say what happens to it. What does it do? And it's a function. It's a function that given a finite set of responses just produces the next generator. And we use V of view, just like the classical papers. The adaptive mechanism, I'm not teaching anyone anything new here. I'm just sort of using a white box approach to this specific mechanism. This is the mechanism just before, right? It gets a generator, gets a sample set, and it spits out a response. His response is a view, but again. And what happens inside is there's one analyst. There is something between 1 and k mechanisms. That's your question. So on one hand, it can be k different mechanisms if I want to deal with that kind of case. In the other case, it can be just one mechanism and then it will be stateful. Anything is possible in this scenario. There is an adaptive interaction between the adversary and the mechanisms. And in order to be coherent, we didn't want the adversary to be in control of the probabilistic aspect because we said the mechanism is the one that has the probability. So the adaptive mechanism just chooses the coin tosses and hands them to the adversary. It doesn't change anything because the internal sub-mechanisms don't know it. And the view, this is a slight change from the notation in the BNSSU. The views only include the responses and the coin tosses at the first coin toss if it was needed. And then every generator is a deterministic function of the previous view, which is important just for the analysis. Okay, so now we can define what's KLSS. So being KLSS means a sequence of K mechanisms which share state, not whatever you want, is KLSS if the adaptive mechanism is LSS. And the theorem states that if any of the mechanisms is epsilon I, delta I differentially LSS, then they all together are the sum of epsilon, sum of deltas, KLSS. The proof itself is relatively tedious, but there's one step there that I think is crucial, and it really resembles what Aaron mentioned before, and that's the idea of looking at the posterior distribution. So, in a sense, that's the way I feel. There are only two real insights here. First, it's understanding that any iteration can be thought of as the first iteration in a world where the prior distribution is the posterior of the previous view, and the mechanism is maybe a slightly different mechanism behaving with all the previous knowledge. So here there was another part of the slide we omitted because it just looked too crowded, but this is not necessarily correct. Here we're assuming that the mechanism depends only on the sample set and the generator, and we say, oh, the generator is a deterministic function of the previous view. If it had internal state, so you would just need to add here, given whatever we know about the process that happened so far. But again, it's just a different kind of mechanism with a different internal distribution. It's a different kind of distribution over the sample sets. This is the Z we used here. And other than that, that's it. So I said two insights. One is every iteration is the first iteration, and then the distances just have triangle inequality. It's a statistical distance over a given set. So basically, that's all that's happening here. This is probably the best time to explain why did we speak about distributions over sample sets and not over sample points. Because even if we started from a distribution that is a product distribution, the second iteration already, the posterior, might not be a product distribution. Therefore, we had to be dealing with generally distribution over sample sets. And another thing, I don't know if I pointed it out clearly enough here, this theorem holds only for mechanisms which were epsilon delta LSS for any distribution. And it's important because we omitted it for most definitions here in the slide, but in the paper we were very, very careful. Most definitions are dependent on, like, I'm accurate or I'm not accurate, I'm stable or anything like that for a given generator, for a given adversary, for a given etc. This one has to be for all distributions. Why? Because we don't know what distributions will be induced by the posterior once we start getting answers. Okay, so what's left? Generalization. So linear queries, I don't need to teach you about that. Only we use the notation of delta bounded linear queries, which are from minus delta to delta, and we use a Q delta. And again, revisiting the definitions of sample accuracy and distribution accuracy, just using now our notations. So again, this is the sample accuracy, this is distribution accuracy. Similar definition for a sequence of queries. We're taking the max norm over all of the answers. It can be either defined relative to just a sequence of queries or relative to an adversary which creates this sequence of queries. Okay, so how do we prove that LSS implies generalization? By almost copying what they did in BNSSU, using the same monitoring mechanism. I painted this in red because, well, almost all of the letters, no, all the letters are here. So you might be upset. First, I omitted the part where because we need the sign to be positive, so we might flip to the minus. And also here there's a slight lie, Q is not part of V in our notation, it's just a deterministic function of it. But up to these two caveats, it's the same mechanism. And just a reminder to whoever didn't read the paper by coincidence. So this mechanism gets an adversary, gets a vector of sample sets, a t sample sets. It runs the adaptive mechanism between the mechanism or mechanisms and the adversary t independent times, and then chooses from all the iterations, from all the queries and responses within the iteration, the worst one. Worst in the sense of the highest distribution inaccuracy. And how does it know it? Because the mechanism, this out mechanism, knows the real distribution. Obviously, it's a contrived example. It's not a normal situation, but it's a thought experiment. The idea is that since we proved post-processing and adaptive composition, so each of these steps is LSS, and since LSS holds under post-processing, it should hold even under post-processing of doing something with the underlying distribution. And therefore, we can prove that even the whole process is LSS, where the degradation is only in the delta parameter, not in the epsilon, because it was independent. So we state this theorem with parameters that are looking a bit funky here, but other than that, it's like relatively classical. If your epsilon delta k LSS and your epsilon delta k sample accurate, your epsilon delta k distribution accurate. The proof, just like a general reminder to which we have. Okay, so I'll just remind what happens here. So we're looking at the expectation of the difference between these two quantities. Okay, so there's the expected sample error, expected distribution error, and expected generalization error. And what we say is that since we are sample accurate and these are t independent iterations, and t is chosen to be order of 1 over delta. So it's t times delta, it's the order of 1. The same thing we prove with LSS, since the probability to get an epsilon unstable response is less than delta, so repeating a t times is less than t times delta. And if you're not distribution accurate, since we're choosing the worst one, so the probability that none of them will be too bad is 1 minus delta to the power of t, which is about 1 over e. It's again the order of 1. So if you play correctly with the factors, you reach a contradiction where you can prove when this by triangle inequality is too small, and here it says it's too big. That's basically the idea of the proof there, and we repeat it. Nothing interesting here. Now to the supposedly interesting part. We claim that it's also necessary and not just sufficient. How do we do that? By constructing a query that actually uses the difference in the distribution. So given a view or a response, it can be the same. We're dealing now with views, so that's why we use this notation. Given a view, we assign delta or minus delta to any point in the domain, depending on if the prior is higher than the posterior or the posterior is higher than the prior. Meaning that the expectation over the domain, given this view or just the prior expectation, will be as far away from each other as we can. And once we do that, we repeat exactly the same idea with the monitoring mechanism. The only change is what do we do after each iteration. So again, we run t independent times the monitoring mechanism, the adaptive mechanism. We get a v. We construct an overfitting query, the loss assessment query, using that v, and we feed it to the mechanism. It's the k plus 1 iteration, and we get a response. And again, we choose the one which was supposed to have the worst overfittingness and output that, and its response. And the theorem says that, very similarly, if you want to be epsilon delta k LSS, if you are not epsilon delta k LSS, you can't be both epsilon delta distribution and sample accurate with k+1 because, again, we constructed one extra iteration. And again, we have the same issue as Uri mentioned, like maybe there's some like weird mechanism that can maintain distribution accuracy and after losing sample accuracy, and then it can do better. But as long as you have to be both sample and distribution accurate, we proved that you must be KLSS. And the proof is exactly the same expectation, same thing, just now these two are bounded from above by t times delta, which is order of 1, and this one is greater than, it's order of 1 also because we chose the worst. Here, the worst is in the sense of the generalization ability. Okay, so just to recap what happened. The problem of generalization guarantee under adaptivity is a well-known problem. There is a whole line of guarantees based on stability notions that started by differential privacy. We propose a new definition of stability, which A, has the properties that are similar to the rest of stability notions, most importantly, post-processing and adaptive composition. And it's both sufficient and necessary for generalization under the assumption of sample accuracy. There are a few more things we were working on which we didn't get to. One is advanced adaptive composition, the same way we have with differential privacy. In a sense, you can almost see what it happened here. I know I don't have this slide, but basically, as I told you, we used a triangle inequality. Now, these are independent in some ways. So as long as you have a bound on the expectation, you can do, again, some trick proposing it as a martingale and using a Zuma inequality. But we don't think there is a guarantee on the expectation that is a direct result of just this definition. We think we have a separating example for max information, right? Until now, I showed that this definition is both sufficient and necessary, but no one said it's not equivalent to other definitions that are known, in particular max information maybe. So we think we have an example where max information, for a mechanism that is not max information and yet it will remain generalizing. And what really bothers us, and we're starting to work on, is providing generalization guarantees directly without sample accuracy. We're not sure about the necessary, but the sufficient, and we're not sure about the sufficient, but the necessary, we think we have an example, proof. The main open, first of all, it opens probably a variety of opportunities and questions. The main ones are first, can we propose any new algorithm or existing algorithm with different parameters that can do better for generalization purposes? We know, using the lower bounds that Uri mentioned, that in the most general case, we can't beat the k-squared parameter, but maybe other dependencies can be improved. More importantly, what happens, one of the aspects of the way we presented everything is that every theorem and every definition might be distribution dependent, might be adversary dependent, etc. So the question is, if we limit ourselves to a family of distributions, if we limit ourselves to a family of queries, or what makes more sense is a family of adversaries. For instance, Adam's open question may be if the adversary doesn't have any information that the mechanism doesn't have, maybe we can have better guarantees. And also there's the issue of extension to other types of queries. Differential privacy was proven also for low sensitivity queries. We didn't do it yet. I'm here for 2 more weeks, and I'll be more than happy to sit and talk with whoever, any of you who will think that it's worth his time. So thank you very much.
Can you go back just to the separation question? Like, I'm not sure what sort of separation you have in mind, but I guess one thing that separates all these information guarantees from generalization guarantees is if you output the first 20 data points for something in the clear. This is like a possibly unbounded amount of information about the data set, but it doesn't really mess with generalization too much. Is that the sort of separation you have in mind, or is it? Are you looking for something a little more?
So what you're mentioning is so. So the question is, what's the distribution you have over the sample sets? I'll just mention, like, in very brief words. Our example is for distributions, even over product distributions, and any kind of product distribution. Basically, the idea is, let's say we have it's a finite, very large set, and the response is basically taking the sample set, breaking it to pieces of size, let's say n epsilon squared. So even knowing it is not enough. And you have a bunch of them. And then also randomly breaking the rest of the domain to pieces the same size. And then releasing this, how do you call it, grouping of the domain. In no particular order, so no one knows which one of them are in the set. What you basically, the only information you revealed is that for each one of these subsets, the sample set either includes all of it or none of it. That's the general mechanism. Now, any distribution, the change in the distribution over the sample sets and the distribution over the sample sets is dramatically, right? Because most of the weight of the distribution was on sample sets that included fractions of these. So you omitted almost all of the distribution. But on the other hand, if n is big enough, greater n is larger than epsilon squared, like it's 1 over epsilon to the fourth or whatever, you can look at it even as just like each one of them is one quantity and still have the classical concentration bounds. So in a sense, what you have is, like, for almost any product distribution in any any product distribution in any domain that is large enough, you can break this max information and still remain with generalization guarantees.
Okay, I'll ask my question again offline. I didn't quite.
Like we already know that, like, compression schemes that, like, release like like learning a real valued interval, right? So it's releasing a single data point, generalizes, but that has unbounded max information. So are you looking for, like, a different kind of separation?
Wait. Okay, so first of all, it's not just generalized. I want generalization guarantees. Here I have generalization guarantees because even after getting all this,
like Uri's notion of post-selection.
So it doesn't contradict the post-selection example. That's because exactly what Katrina asked at the end of the talk. There's a very delicate thing about what happens when you deal with order. So either you deal with ordered sets, if the ordered sets are defined in advance, so then you need to define what exactly is accuracy. Because is the order, can it play a role in accuracy or not? And if the order is defined in a synthetic way, for instance, we take part of the bits and say, ooh, that defines order, then you're not low sensitive. So if you're using, so in the way we presented all of it, you can either choose to have the sample sets ordered or not ordered, it doesn't matter, but then it's careful to define what is accuracy in this case, because
maybe we should take this offline.
okay.
Just a very quick comment. I mean, we do know there are natural mechanisms which are not sample accurate, but generalized. For example, mechanisms that first use, say, one part of the subset until they see that they start overfitting on that, and then use the other one to answer queries once they see that there is already too much overfitting on the first part. So these mechanisms will not be accurate on the entire samples because they're maybe only accurate on a fraction of it and overfit a lot on the other. Just
right.
I just think that these mechanisms, it's proving things about these mechanisms. I mean, there is interesting stuff beyond the mechanisms which are sample accurate.
Right. And we tried to play with a few things. The problem is a lot of the times you can model these mechanisms as a bunch of sub-mechanisms interacting between them, and then, okay, so you have the guarantee broken for each one of them. And if not, but yes, it's a big question. The main thing is that it feels very natural that if the mechanism, if you have an overfitting query, all you need to do is to make sure the mechanism can't know if now you're proposing an overfitting query or not, and then he doesn't know if to believe the data or not. Right? If you manage to figure that one out, that's it. You don't need to deal with sample accuracy. The question is, well, we didn't find this a way to prove that the mechanism can't tell if it's one of the overfitting queries or not.
Let's thank Moshe again.